In this video, we're going to take a look at some properties of limits. Okay, so our first property deals with adding and subtracting. So if you were ever finding the limit of the sum or difference of two functions, so notice here we're not just dealing with one function anymore, okay, we're dealing with two functions. If we were trying to find the limit as x approaches c of f of x plus or minus g of x, what we can do is find the sum or difference of the limits. Okay, so it kind of goes like this. If you were evaluating the limit of a sum or difference, you just make it the sum or difference of the limits. Okay, so we could just evaluate the limit as x approaches c of f of x, evaluate the limit as x approaches c of g of x, and then add or subtract the two numbers. Okay, our second, and actually I'm gonna, on that thought, I'm gonna skip down to number 3. If you are multiplying, because it's very similar to addition and subtraction, if you're multiplying, so if you're evaluating the limit of a product of functions, so the limit as x approaches c of f of x times g of x, then that would be equal to the product of the limits. You can just find the limit as x approaches c of f of x, find the limit as x approaches c of g of x, and then multiply the two numbers. Okay? Same thing with division. If you are evaluating the limit of a quotient of functions, so the limit as x approaches c of f of x divided by g of x, you can just find the quotient of the limits. So you would find the limit as x approaches c of f of x, find the limit as x approaches c of g of x, and then just divide. Now, we have to add a stipulation here, since we cannot divide by 0, you know, this would not work if the limit as x approaches c of g of x equals 0. So, we're, you know, this property works as long as the limit of the denominator does not equal 0. Okay, so honestly, the addition, subtraction, multiplication, and division property, they're all pretty similar. It's the same idea with the 4 different operations. All right, let's go back to number 2 now. We have what's called a constant multiple property. And you guys, sometimes we call these laws as well instead of properties. So if you hear me say limit laws, you know, or the constant multiple law, that's why. But this one says, if you are evaluating the limit as x approaches c, and you have some constant, which we're just calling k, times a function, which we're calling f of x, then what you can do is you can move that constant in front of the limit. So it would equal k times the limit as x approaches c of f of x. Okay? So just to kind of give you an example here, let's say you were evaluating the limit as x approaches 3 of 2 times f of x. You could just move the 2 in front of the limit. So this would be equal to 2 times the limit as x approaches 3 of f of x. Okay, now let's go down to number 5, exponentiation property. If you are finding the limit as x approaches c of a function raised to a power, then you can just find the limit of the function, take that number, and raise it to the power. Okay? So if you're evaluating the limit of a function raised to a power, you can just make it the limit of the function raised to that same power. Okay, and then our last one is dealing with compositions of functions. So, if we know that the limit as x approaches c of g of x equals L, and let's say we want to find the limit as x approaches c of f of g of x, then what you do is if you guys remember with compositions of functions, like when you're evaluating a composition, how you always start on the inside of so like if I were evaluating this composition of functions, f of g of x, I would find g of x first, and then evaluate f of that number. It works the same way with the limits. Okay, I would find the limit as x approaches c of g of x. That would equal L. And then it would become the limit as x approaches L of f of x. And we'll look at some examples. That one can be a little bit more confusing, and I want to add a number 7. If you are asked to find the limit of a constant, then the limit would always equal the constant. I'll give you an example. Let's say you're evaluating the limit as x approaches, I don't know, 2 of some constant, which I'm just going to use 5 as the constant. And that limit would equal 5. Okay? Keep in mind, if a function is constant, like if our function, let's call it f of x equals 5, then that graph is a horizontal line that intersects the y-axis at 5. So no matter what x is approaching, y is going to always be approaching 5. Okay? And it would work out in a similar fashion anytime you're evaluating the limit of a constant or a constant function. Okay? Okay, so in general, what we are doing here when we use these properties is the limit can be taken of each piece, including a variable, in any expression independently. Okay? The results of these limits then can be combined using the algebraic rules of the expression. So notice what happened here. Using our limit laws, like we were evaluating the limit as x approaches c of the square root of 3x plus f of x, all divided by x times g of x squared. So using our limit properties, notice that we end up just putting our limit notation in front of any variable, in front of any function. So notice how we were able to kind of break that apart into individual limits. Then we can evaluate those limits and then just follow the algebraic rules of the expression to get a final answer. Okay? Now, there is one important thing to note. If, when using these properties for a general two-sided limit, if you encounter D and E, okay, if you find that the two-sided limit does not exist, then you must split up the limit into the left and right-handed limits and reapply the properties. It goes back to the existence of a limit theorem that said in order for the two-sided limit to exist, the one-sided limits must both exist and equal each other. Okay? So if you ever find that the two-sided limit does not exist, initially, evaluate your one-sided limits, because you might find that your one-sided limits are the same. And if they are, that means the two-sided limit does in fact exist and would equal that value. Okay, let's look at some examples. So, you guys, I kind of like to call these generic problems because the information we're given some limits, but we really don't know much about functions. Okay, so for instance, we are told that the limit as x approaches 3 of f of x equals 8. But I don't really know much about the function f of x. But that's okay. I know what this limit is equal to. And we're told that the limit as x approaches 3 of g of x equals negative 2. And the limit as x approaches 3 of h of x equals 0. Okay, so in example A, we want to find the limit as x approaches 3 of 2 times f of x minus 4 times g of x. So I'm actually going to use two different properties here. I'm going to use the constant multiple property, because 2 is a constant multiple and 4 is a constant multiple. And then I'm also going to use that difference property. So this would actually break up into 2 times the limit as x approaches 3 of f of x minus 4 times the limit as x approaches 3 of g of x. And I'm actually going to work this across the paper, so I'll call that a. So notice what I really did there. Using the properties allowed me to put that limit notation just in front of both functions, okay? And keep in mind that they tell us what these limits are equal to. So from here, we're just substituting. I know the limit as x approaches 3 of f of x equals 8. So I will substitute 8 in place of that limit, minus 4 times, and I know the limit as x approaches 3 of g of x equals -2. So I will substitute -2 in place of that limit. And then now we're just down to order of operations. So we'll end up with 2 times 8 is 16. -4 times -2 is +8. 16 plus 8 equals 24. Okay, let's look at B. So here we're evaluating the limit as x approaches 3 of 2 times g of x all squared. So again, my limit properties allow me to break this apart where I can, and I'm actually going to keep my brackets. The 2 is a constant multiple, so I can put the 2 in front of the limit as 2 times the limit as x approaches 3 of g of x. And then I can square that value, okay? So I also used two properties here. The constant multiple property allowed me to put the 2 in front of the limit. And then I also used that exponent property that says I can evaluate the limit of the function and then raise it to the power, okay? All right, so now we're just going to substitute. I know that the limit as x approaches 3 of g of x equals -2. And now we're just down to order of operations. 2 times -2 is -4, and -4 squared is 16. Okay, let's look at part C. Okay, this one's a little bit more involved, but that's okay. Again, the limit properties allow me to just put that limit notation in front of the functions, okay? And I can, look at the expression and see I have an f of x, a g of x, and an h of x. But that's okay. All right, so I would end up with the cubed root of the limit as x approaches 3 of f of x all over the limit as x approaches 3 of g of x plus 4 times the limit as x approaches 3 of h of x. Okay, all over. Now remember, x plus 7, that is a function. So I'm just going to put my limit property, or my limit notation, the limit as x approaches 3, in front of the x plus 7. Okay, then we can do some substituting, because again, they told us what these limits are equal to. The limit as x approaches 3 of f of x equals 8. So this will become the cubed root of 8 divided by -2 plus 4 times 0 all over. Okay, now let's talk about this limit as x approaches 3 of x plus 7. We could take a graphical approach to this since we've been working on evaluating limits graphically. X plus 7 is a linear graph. The x-intercept would be 7 and the slope would be 1. So I don't know, let's just say this is our line. So when x is 3, If x is approaching 3 from both directions, what is y approaching? Well, that would actually end up being 10. Maybe I didn't draw this exact. That's okay. So another way we could just find it, notice that we would also get 10 by just plugging in 3 for x. 3 plus 7 equals 10. So that might be an easier way to approach that one. Okay, so let's keep going. Cube root of 8 equals 2. Now 4 times 0 is 0. Okay, now we're going to end up with 2 divided by negative 2, which equals negative 1, plus, well, 0 divided by 10 equals 0, and negative 1 plus 0 equals negative 1. So we end up with negative 1 in the end, after lots of work. Okay, now we can also use these properties if we're given a graph for each function. So notice here we're given a graph for f, and we're given a graph for g. All right, now we're going to start these the same way we did in previous examples. So let's start with A. If I want to find the limit as x approaches 0 of 2 times f of x squared plus 3 times g of x, I'm going to use my limit properties, and I'm going to put that limit notation just in front of the functions. Okay, so this would end up looking like 2 times the limit as x approaches 0 of f of x, all squared, plus 3 times the limit as x approaches 0 of g of x. Then we are going to substitute, okay, but we've got to use our graphs to evaluate these limits. Okay, so I got to find the limit as x approaches 0 of f of x. So I'm going to go to my graph of f. When x is approaching 0 from the left and from the right, I can tell that y is approaching 2. So this would equal 2 times 2 squared, okay, plus 3 times. And now I've got to evaluate the limit as x approaches 0 of g of x. So I'm going to go to my graph of g, and I can see that as x approaches 0 from the left and from the right, y is approaching 0. All right, order of operations, 2 squared is 4, 4 times 2 is 8, plus 0, which is 8. Okay, let's look at part B. All right, so again, we're evaluating the limit as x approaches negative 3 of x squared times g of x, all divided by f of x. Now, x squared is a function, okay? So I am going to have to put that limit notation in front. Okay, times the limit as x approaches negative 3 of g of x, all divided by the limit as x approaches negative 3 of f of x. So again, all I'm doing is putting that limit notation in front of all of the functions, and then we'll perform the operations. Well, after we evaluate the limits. Okay, now, to evaluate the limit as x approaches negative 3 of x squared, you guys, x squared is a parabola. There's nothing too unusual in the graph of a parabola, meaning there are no holes, there are no vertical asymptotes. So really, when I evaluate that limit, it would be the same as evaluating the function at negative 3. So I really can just plug negative 3 in for x. Okay, so we'll end up with negative 3 squared times, okay, now to evaluate the limit as x approaches negative 3 of g of x, I'm going to have to go back up here to my graph. So let's see, here's negative 3 on the x-axis, and so if I'm evaluating the limit, I can see that my y value is getting closer to 1. Okay, all over, and then we have to evaluate the limit as x approaches negative 3 of f of x. So again, here's negative 3 on the x-axis. So if x is approaching from both directions, I can see that y is approaching negative 1. Okay, and then if we just work this out, negative 3 squared is 9, 9 times 1 is 9, divided by negative 1 equals negative 9. Okay, let's look at part C. Okay, now this time we're faced with a composition. Okay, so we want to find the limit as x approaches negative 3 of g of f. So what we're going to do is we're going to start on the inside. We're going to evaluate the limit as x approaches negative 3 of f of x. Okay, now we actually just did that. We can see that the limit as x approaches negative 3 of f of x equals negative 1. Then, that then becomes the limit as x approaches negative 1 of g of x. Okay, so this is now our new value that x is approaching. Okay, so let's go over here. When x approaches negative 1, I can see y is getting closer to positive 1. So that's our final answer for that composition. Okay? All right, I've got a few more examples graphically. And actually, guys, I think just to shorten the video, I'm going to jump to example G, because I think you're probably getting the idea here. But there's one thing I need to point out. So let's say that we start by evaluating this limit, and we're finding the limit of a product. So remember, our properties allow us to make that the product of the limits. Okay, and then I'm going to go to my graphs. Now the limit as x approaches 2 of f of x. Okay, here's 2 on the x-axis. But notice, as x approaches 2 from the left, y is approaching 1. And as x approaches 2 from the right, y is approaching negative 1. So like your first thought would be, oh, well, okay, this two-sided limit does not exist because the one-sided limits are not equal. And that might lead you to the conclusion that the product does not exist. But that may not be the case. So this is when you need to evaluate the one-sided limits. Because if the one-sided limits are the same, then the two-sided limit does exist. Okay? So let's just make this a one-sided limit and see what happens. So I'm just going to start from the left because I feel like it. Okay, so let's start from the left. The limit as x approaches 2 from the left of f of x, okay, that would equal 1 times the limit as x approaches 2 from the left of g of x. Now 2 from the left of g of x, we can see that y is approaching 0. And 1 times 0 equals 0. Okay, let's evaluate the limit as x approaches 2 from the right. All right, the limit as x approaches 2 from the right of f of x. Again, we can see that y is approaching negative 1. The limit as x approaches 2 from the right of g of x. We can see y again is getting closer to 0. Negative 1 times 0 is 0. Okay, our one-sided limits, they both exist and they are equal. So we now know that our two-sided or general limit does exist and it equals 0. Okay, so if you find when you're using these properties that one of these limits does not exist, you have to fall back to our existence theorem for a two-sided limit. You have to evaluate the one-sided limits. All right, you guys, we'll definitely practice this some more in class tomorrow. As always, thank you for watching and have a good night.